Anytime that we start dealing with functions, there are certain characteristics that we always care about, and they're bulleted there for you. You can pause for a moment and read those. We'll talk about them in more detail in just a second. One of the things that you should be familiar with is the concept of a zero of a function. And a zero of a function is an x value input that causes the y value output to be a zero. And to be really specific about that, if you just thought about any generic kind of a graph with the x-axis and the y-axis, and at this point where the graph crosses the x-axis, that's a certain x value that causes the y value to be a zero. That's why it's called a zero of the function. Now, sometimes you'll see older literature refer to that as a root. I don't think that standardized tests do. They always call them zeros or x-intercepts. But in the early days of graphing, we're talking about, 1600s, then they imagined that this was like a tree, and underneath the ground are its roots. So the roots begin right as it hits the ground. So that's why that point's called a root, and it has nothing to do with mathematics. So here's the things that we can see. Whenever we have a standard form equation, that's considered to be the simplest algebraic form, but it doesn't reveal much about it. For instance, if I input an x value of 0, then you can see that everything goes to 0 except the c. So that means that this c point is the y-intercept. And I know that when I expand the vertex form of the graph, that multiplier that tells me about the shape and opening of the graph distributes onto the x squared. So that a value there will tell me the direction of opening, but it doesn't tell me much beyond that. And when I put it into its factored form, if we set it equal to 0, we're asking what x value input causes a y value output of 0. And as we solve these two factors equal to 0, those represent the x-intercepts, or the zeros. So it'll tell us what the zeros are, and if we just imagine first times first, it would actually be ac times x squared. Whatever this number is here, whether it's positive or negative, will tell us whether it's upward opening or downward opening. But it doesn't reveal much beyond that. It doesn't tell you about the axis of symmetry or the y-intercept, any of those. Now, the graphing form, sometimes called the HK form, sometimes called the function form, it'll tell me a lot about my graph. So what it will tell me is the left-right shift, the up-down shift, the direction of opening, and that left-right shift also represents the line of symmetry. But it won't tell me where the zeros are, and it won't tell me what the y-intercept is. So each one of the forms reveals some things, but doesn't reveal everything about the graph. And you're supposed to know everything about every graph. So if I want to know where the y-intercept is, I simply ask, what's the x, when I input x value 0, what's the y value output? And I can do that with any kind of form on the function, the factored form, the HK form, the symbolic form. Just input a 0 and see what happens. If I want to find the zeros of the function, then I have to set the function rule equal to 0. So I want 0 to be the y value output, so I just have to solve that function rule equal to 0. Some are easier than others, obviously, but that's what we would do. And if I want to find the vertex and axis of symmetry for a function that's in factored form, then I need to recognize this. When I graph a parabola is a symmetric figure. And that line of symmetry holds the vertex. And the distance from either side, I didn't draw it in scale, sorry. The distance from either side of that line of symmetry to those x-intercepts, or those zeros, is the same. So I can reverse that And if I know what the two zeros are, I can find the midline of that. And then whatever that x value is at the midline, I can always evaluate the function at that point, and that'll be my vertex. And we'll see that in a couple of examples. So with that in mind, let's just look at some examples and see what we can do with them. So the first thing that we should always look for is to see if we can factor it. And this can factor with ease. So I would have an x minus a 5 times an x minus a 4, an x minus a 1. And instantly, if I set it equal to 0, then I could see that the values of x that create the expression to equal 0 would simply be an x value of a 5 and an x value of a 1. So I know my graph crosses at x value 5 and an x value 1. Now here's a shortcut, and you should know it from all your years in school. You're looking for a number that's halfway between two others, and the way that you do that with ease is you average the two numbers. You simply add them up and divide by 2. So that would be a 3. What some people will do is they'll take the gap between them. 1 to 5 has a gap of 4. They'll split the gap in half and get a 2. But remember, what that tells you is that you have to move right of 1 by 2 units to get to 3, or you have to move left of 5 by 2 units also to get to 3. But the easiest way to find that axis of symmetry is that. Now, since I know the axis of symmetry, I know that vertex sits on the axis of symmetry, and I've determined that that x value for the axis of symmetry is a 3. So all I have to do is to evaluate f of 3. So that would simply be 3 squared is 9, minus 4 times 3 is 12. My running total now is negative 3 minus 5. So that would be negative 8. So I know that my graph is, that doesn't seem right. 9 minus 12 minus 5. 9 minus 17, negative 8. That seems right. Except it doesn't seem right for, oh dear, what have I done? Here's the first example we're going to look at, and we should be able to tell that it has an obvious factoring, and the obvious factoring would be an x minus 5 and an x plus 1, and if I set it equal to 0, that would give me obvious solutions of x equals 5 and x equals negative 1. So those 2 points are where the x value inputs that cause the y value outputs to be a 0. So with that in mind, how do I find the vertex? Well, halfway between that would be an x value of, well, here's a shortcut for you. When you're looking for the number halfway between two others, you simply average the two numbers. You add them up and divide by 2. So that would be an x value of 2. You can tell that x value 2 is 3 units from either of those intercept points, those x-intercepts. And my vertex sits on that line of symmetry somewhere. So all I need to do is to evaluate at x value 2. So I would get a 2 squared is a 4, minus a 4 times a 2, that's a minus 8, and minus a 5. So 4 minus 8, negative 4 minus 5 is negative 9. So I know my vertex point sits down here at x value 2, y value negative 9. And by the way, if I wanted to, I could take that information and tell you that my function would be an x plus 2 squared minus 9. And I had to be able to confirm real quickly, whoops, not a plus 2. What am I thinking? An x minus 2. And I can confirm really quickly, first term squared is the x squared, twice the product is the minus 4x, second term squared is a 4, minus 9 is the minus 5. So I can confirm real quickly that that's the correct HK form for that function. So the domain is the set of all real numbers. So I can say it several ways, like this, or I could say that x could be anything from negative infinity to positive infinity. Either way is fine. And the range, well, I know that the range over 1, up 1, over 2, up 4, over 3, up 9. By the way, that over 3, up 9 confirms these 2 points up here. Over 4, up 16 would be these points here. And there's my parabola. And moreover, one of the things that you should see is the range is y values above -9, including -9. As an algebraic inequality, I'd say y is greater than or equal to -9. In interval notation, I'd say that my y is anything from -9 included without limit going up. The increasing interval is everything to the right of 2. So the increasing interval would be 2 and to the right. And the decreasing interval is left of 2. So the decreasing interval is from -infinity up to 2. And the y-intercept, we could have told that y-intercept originally right here. The y-intercept is 0, -5. So that standard form can reveal that to us instantly. And the zeros we've already found. The zeros are at x is equal to 5 and x is equal to -1. Also, you can tell your zeros by just stating them in point coordinates, 5, 0, and -1, 0. Either one is fine. By the way, that's always why we have to put the element symbol when we talk about interval notation. Up with the interval notation, those aren't xy coordinates. Those are beginning and ending points. Whereas on the zeros of the function, they're actually xy coordinates. So that's everything there is to know, and we can find it pretty quickly. Now, we should try to see if this thing can factor, and you should tell pretty quickly it can't. The half times the 7 is 7 halves, and there's no factor pair of 7 halves that's going to somehow combine to make the -4. So that's the test for factoring. So I need to get it into its HK form. So I'm going to use all the skills that I have and the ones that you developed just recently. So I know that when I expand this binomial, that it's going to take this constant right here and double from the expansion of the binomial, and then times it by half. Well, doubling and halving is reverse. So if this is a -4 up here, this will be a -4 down here. But let's prove it. And the way that we prove it is really pretty simple. All we have to do is just start expanding and just talk it through. So as I expand, I'd say first term squared, x squared times the half x squared, check. Twice the product, -8x times the half, I'm back to -4x. Second term squared, 16 times a half is 8, but I wanted a 7. So that -1 turns the 8 into the 7. So the vertex then is at 4, -1. And again, the domain, I'm just going to be lazy and say all real numbers. The range, well, I can see that it's upward opening because the coefficient on x squared is positive. So that means at x value 4, y value -1, that it's an upward opening parabola. So the lowest value on the range is -1, and then it is everything above that. So I'm going to say y greater than or equal to -1. And let's go ahead and get some points. Normally I'd go over 1 and up 1, but I'm only going to go half as far in the vertical. Over 2 up 2, over 2 up 4 becomes over 2 up half as far. Half of 4 is 2. Over 3 up 9 becomes over 3 up 4.5. So 4.5 would take me to this point and this point. Over 4 would normally take me up 16, but now it's only going to take me up 7. So it takes me to here and to here. So just for fun, just to demonstrate that we're right, notice that this is the y-intercept at x value 0, y value 7. Let's see what happens with an x value of 0. Oh, we don't need to, do we? Because there's the 7 right there. But watch, just to show that our transformation was correct. What is half of 7 minus 0? Let me get it right. The coordinates of that vertex were 0, 7, so I'm inputting a 0, and I hope that the output is going to come out as 7. So let's see if it is. 0 take away 4 is 4, squared is 16, half of 16 is 8, 8 take away 1 is 7. That's a proof that my algebraic transformations were correct to get it into that graphing form. So I can see that the increasing interval is everything to the right of 4. Ooh, I hate it when I make bad drawings. So increasing interval, everything right of 4. And remember, you're supposed to include that vertex point in the increasing interval. And so the decreasing interval is everything up to 4. So for x values less than or equal to 4, the decreasing. The y-intercept we already decided was a 0, 7. And the zeros, ooh, what are those zeros? So here's where it becomes really important to notice that this work that we did over here with our transformation into the HK form, the zeros of the function are the x value inputs that cause the y value outputs to become 0. So in sequence, we say x subtract 4, then we square, then we multiply by half, then we subtract 1. The last thing done is the first thing undone. Add 1 to both sides. 1 is equal to 1/2 times x minus 4 squared. So again, x minus 4, then squared, then times half. So now I'm going to double both sides to reverse the effect of the half multiplier. 2 is equal to x minus 4 squared. Take the square root. Don't forget the plus minus. So x minus 4 is equal to plus or minus the square root of 2. Move the 4 to the other side. X is equal to negative, I'm sorry, not to negative. X is equal to 4 plus or minus the square root of 2. So one of the things that you need to remember in that quadratic formula is that old negative b over 2a defines the axis line, and that square root of 2 distance right there is the distance from that axis line to the two x-intercept points, the solution points or the 0 points. So the zeros, I could list them just as the 4 plus or minus square root of 2, or I could list them as points. And when I list them as points, you get to be kind of quick and easy, and you have to realize that that's actually two separate points. 4 plus the square root of 2, 0, is this right-hand intercept point. 4 minus the square root of 2 is this left-hand intercept point. So one other type of a problem that you're going to see is when you see a picture of a graph and you still have to find all that information out. It looks like that y-intercept point might be a 3, but don't just go on looks. We have to show all the processes. Now the easy thing to see here, remember when we think about a parabola, we think about how far over and how far up it goes. It goes over 1, up 1. It goes over 2, up 4. It goes over 3, up 9. That's what I want to look at right here. When I'm 3 off the vertex, it's supposed to be up 9, but this is only up 6. So I asked myself the question, this 6 units right here, is it normal? Is it many times bigger than normal, or is it a fraction of normal? And the answer is it's a fraction. It's 6/9 of normal, which reduces to 2/3. So what that means is that my equation is 2/3 and then the parenthesis squared. If I have a right shift of 4, that's a -4, and I have a downshift of 8, so that's a -8 for the outside. So we can see the vertex, they just handed it to us on a silver platter. The vertex is 4, -8. By the way, that 4, -8 is what allowed us to write this equation. The domain, all parabolas have a domain of all real numbers. The range is everything above -8. I think I'll do it just for fun as this. That's an interval notation. The increasing interval is everything to the right of 4. So I think I'll do more, element of. That x is an element of 4 moving to the right. That's where it is increasing. And then from -infinity until it gets to 4, it was a decreasing function. What about that y-intercept? Well, to find the y-intercept, I plug in 0 and see what happens. I think I can do that in my head. But you'll notice that it's not going to be the number that it looked like maybe it would be on the graph. It looked like maybe it would be a 3. But the y-intercept is 0 take away 4, -4, squared 16 times 2/3. That's 32/3 take away 8. So that's 32/3 take away 24/3, which is equal to 8/3. So the thing to notice is that 8/3 is 2 2/3, about a 2.67 or so. So mathematically, we like that perfect little fraction. And you can tell it's almost impossible to tell on the axis whether that was going to be a 3 or just around 3. Now we know. Now, whenever it's time for us to find the zeros, we always do it the same way. We wonder what's the x value input that causes the y value output to equal 0. So, just like last time, we're imagining all the steps in reverse. Whoops, that's a square. So I'm going to add 8 to the other side. Then I'm going to multiply by the reciprocal, 3/2. Half of 8 is 4, so this 3/2 becomes a 12, is equal to x minus 4 squared. Then I take the square root. I'm going to go ahead and simplify. 12 is 4 times 3, so the square root of 4 is 2 square root 3. And then I'm going to add the 4 to the other side, and I'll have x is equal to 4 plus or minus the square root of 3. So again, I'm going to say that there's 2 points, 4 plus the square root of 3, or 4 minus the square root of 3, create an output of 0. And remember that same idea again, that there's the axis of symmetry, and that square root of 12, or that 2 square root of 3, is that distance that we see between the axis of symmetry and those 2 intercept points there. So it's supposed to go pretty quick and easy. It will with practice. You really have to kind of focus on what principles are driving each little step of that process. So just practice is all I can tell you, and the more problems you do, the more natural it becomes. Good luck.